let's start with the assignment 5. If a is positive, you have to prove that first integration from minus infinity to infinity cos x over a square minus x squared dx is equal to pi sine a over a. And then secondly, you have to prove integration from minus infinity to infinity sine x over a square minus x squared dx is equal to 0. So you have to prove these two results. Let's start with the proof. Now because I'm having cos x and sin x in the numerator, so I have to change them in e the power iota z. Here m is equal to 1. So we will integrate the function fz equal to e the power iota az, where a or m, this is equal to 1. So I write e the power iota z over a square minus z square. This function we have to integrate. Now if you take the denominator equal to 0, I get two poles, that is z equal to plus minus a. So if we integrate this function along the contour, then this contour is indented at 2 points, z equal to a and z equal to minus a. Now here if you look at this contour, this is indented at z equal to minus a and a. So this is your semicircle gamma 1 with radius rho 1, and this is the semicircle gamma 2 with radius rho 2. And this curve is in clockwise direction. So the first angle is pi and the second angle will be 0, right? And if you look at the points, this is minus r and this is plus r, where r is the radius of this bigger semicircle tau. And what is this point? This is negative a minus rho 1, because this minus a is from this 0 distance. The distance is between 0 and minus a, this distance, right? And you just have to add this small radius to get this point, and this is negative rho 1, right? So if you add minus a and minus rho 1, you get minus a minus rho 1. And then this point is, you have to subtract the radius now. So this is minus a minus of minus rho 1. So the difference will become minus a plus rho 1, right? And then I'm having the point a here. Here the radius is positive along the real axis. So this point is, this complete distance is a. So you just have to minus this radius, which is rho 2. So to get this point, this is a minus rho 2. And then this point is this complete a plus this distance, which is again rho 2. So this point is a plus rho 2, right? Okay. So because the function is analytic inside and on contour C, and all the poles lie outside the contour, so by Cauchy's theorem, the integration over the whole contour fz dz is equal to 0. And now this contour C is splitted into so many parts, from minus r to minus a minus rho 1. Then the contour is along gamma 1. And then the contour is along again the real axis, minus a plus rho 1 to a minus rho 2. And then again this is gamma 2 semicircle. And then again along the real axis, a plus rho 2 to plus r. And then followed by a semicircle tau from plus r to minus r. Please again and again remember, whenever you have to integrate along the real axis, you have to keep your function in terms of x. And whenever you integrate along the curves, you have to keep your function in terms of z. So when integrating along the real axis, I write the function in x. And then along this curve gamma 1, the function is fz dz. and then along the x-axis it is fx dx. Then for this second semicircle it is fz dz. Again, then real axis I'm having fx dx, and then the semicircle tau, that is again a curve, so this is fz dz equal to 0. And in these cases you have to take r very large. Here r is very large, so you have to take r tending to infinity. And for the smaller semicircles you have to take their radiuses tending to 0. So I calculate this integral, and gamma, this integral is always equal to 0 by Jordan's lemma, right? And let's calculate the integral over gamma 1 and gamma 2. So first, limit rho 1 tending to 0 for first semicircle gamma 1, integration fz dz, this is equal to, the formula is iota theta 2 minus theta 1, theta 2 is 0 minus theta 1 is pi into limit z tends to, where it is indented at z equal to minus a. This gamma 1 is indented at z equal to minus a. So here I write z tends to minus a, then z minus that point minus a, which become z plus a f of z. So this is minus pi iota limit z tends to minus a, and then this is z plus a, putting the value of the function, that is e the power iota z over a square minus z square. So a square minus z square, I know that this is equal to a minus z and a plus z. So z plus a will be cancelled with this a plus z. So this is equal to minus pi iota limit z tends to minus a. This is cancelled, so this is e the power iota z over a minus z. Now putting the value of z equal to minus a in places of z, so you get minus pi iota. This is e the power minus a iota over a minus minus of a, that becomes 2a. So this is the value for the integral over gamma 1. Now calculating the value for the integral over gamma 2, and in that case the radius will be tend to 0. So rho 2 is tending to 0. So limit rho 2 tending to 0, where rho 2 is the radius of the semicircle gamma 2. This integration fz dz is equal to, again the same formula, iota theta 2 minus theta 1 limit z tends to, now this semicircle is indented at z equal to a. So writing z tends to a and z minus a, because it is z minus z naught, here z naught is a, f of z. So this is minus pi iota limit z tends to a, z minus a. So fz is e the power iota z over, this is a square minus z square. Now because here in the formula I am having a minus z, I need z minus a. So just take negative outside, minus pi iota limit z tends to a, z minus a, e the power iota z. I am taking negative outside, so this becomes z minus a and z plus a, or a plus z. So this will cancel out, this negative cancel out with this negative sign, and this is pi iota, putting the value of a now, this is e the power iota a over 2a. So this is the value for the second semicircle, the integral along the second semicircle. Now along the tau. Now since 1 over a square minus z square tends to 0 uniformly as z tends to infinity, and this is meromorphic function in the upper half plane as it has no singularity there. So by Jordan's lemma, limit r tends to infinity, this integral over tau e the power iota z over a square minus z square dz, this is equal to 0, which means limit r tends to infinity, integral over tau, this function is in terms of z, so writing fz, dz is equal to 0, where fz is e the power iota z over a square minus z square. Now in the main equation, in this equation, letting r tends to infinity, rho 1 tends to 0 and rho 2 tends to 0, right? So when r is tending to infinity and rho 1 is tending to 0, I get minus infinity to minus a, right? This limit for this integral. And then here I get minus a to a, integration from minus a to a, because rho 1 and rho 2 both are tending to 0. And then here I get the limits as a to plus infinity, right? So letting rho 1 tends to 0, rho 2 tends to 0 and r tends to infinity in 1, and then put all these values over there, we get first integral minus infinity to minus a f of x dx. Then the value for the integral over gamma 1 we have already calculated, and that is equal to minus pi iota e the power minus a iota over 2a. And then this is from minus a to a f of x dx plus the value for the integral over gamma 2 is pi iota over 2a e the power a iota plus integral from a to infinity f of x dx plus 0. The integral over tau is 0. This is equal to 0. Alright. Now taking these two to the other side and taking pi iota over 2a common, we get, and also merging these three integrals together because the integration is from minus infinity to minus a, then minus a to a, then a to infinity. So completely I'm writing minus infinity to infinity f of x dx. So this is equal to pi iota over 2a, which is common. So this is e the power minus a iota minus e the power a iota. Right? Okay. Do you remember the formula for sine of a as sine of a is equal to, we know that this is e the power iota a minus e the power minus iota a, or a iota, whatever way you want to write, e the power minus e the power a iota minus e the power minus a iota over 2 iota. So in this formula, I'm having e the power a iota positive. Here I'm having negative sign, right? I have to use this formula. So taking this negative sign outside. Now is it okay? Okay. Now putting the value of this from here, from this formula, I get minus infinity to infinity. Writing the value of fx as e the power iota x over a square minus x square dx. So this is equal to, this will become minus pi iota over 2a and instead of this e the power a iota minus e the power minus a iota, this will become 2 iota sine of a, right? 2 is cancelled out, and iota into iota is iota square, that is minus 1, which is cancelled with this. So this is equal to pi sine of a over a. Fine? Alright. Now to get the required results, the first one and the second one, please note here, if we equate the real parts, I get cos in the numerator. If we equate the imaginary part, I get sine in the numerator. So when I equate real parts, I get, because e the power iota x is cos x plus iota sine x. So when you equate the real part, I get cos x over a square minus x square dx equal to, now here real part is pi sine a over a. Hence prove the first result. Alright, now equating the imaginary parts, I get minus infinity to infinity sine of x over a square minus x square dx equal to, now here there is no imaginary part in the right hand side, that is 0 then. So now I have proved these two results, right? Okay. Thank you so much for watching this video. Do like and subscribe for the latest videos. Thank you. God bless.